If not, I'll just switch over to my computer. Anyway, so I was saying, this red box, well, maybe this won't be such a big deal. Anyway, this red is supposed to represent tuning different parameters. Here's phase 1, here's phase 2. Can you guys hear that feedback, by the way?
A little bit, but I think it's just like a laggy connection, probably.
Okay. Anyway. Okay, whatever. So we have these different regions of parameter space, and instead of trying to classify what these kind of phases are by looking at what is happening inside of these phases, we can try instead to classify the ways of going between different phases. So we might try to think about all possible ways to go from some phase like 1 to some phase like 2. So to try to classify all possible things that can happen along this line. And when we do that, we kind of, there are kind of two classes of ways to go between one phase of matter to another, right? One way of going from one phase to another is a first order transition. When you have a first order transition, you have some parameter g that you're using to tune between two phases, and the free energy, if you plot as a function of g, kind of looks like this. It kind of sharply goes between two different phases. So here might be phase 1, right? Here might be phase 2. And first order transitions are not very interesting because they're the kind of stuff that's going on in phase transition is totally invisible away from the critical point, right? So there's some critical value of g here at which you go from one phase to the other. But if I'm starting from phase 1 here and I'm tuning g, and at phase 1 blah 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 blah, and I get GC, and most of that is 1 phase 2. Goes to phase 2. The free energy just kind of is this. And when you have a first order transition based away from the critical, there's just this there's zero in coupling constant space where you just go.
So I think you're maybe a little laggy, Ethan. So can everyone turn off their video, maybe including Ethan, and we'll see if that helps.
Yeah, I tried to. My iPad and my computer are on different wireless networks, so this was supposed to alleviate the problem, but well, okay.
It is better now, though.
Has there been any appreciable change? Okay.
Yeah, it seems better.
Okay, maybe we'll. You can see the F versus G little picture.
Yeah, we can see that.
Okay. Okay. Anyway, so we have first order transitions, and then we also have second order transitions, or where second really means not first, it could be third, fourth, whatever. In second order transitions, this is not what happens. And in second order transitions, you have you kind of go smoothly from one phase into the other. And these are more interesting because they kind of extend into more region of parameter space than just the critical point, right? In second order transitions, you have degrees of freedom that go critical, meaning that they have correlation functions that extend over long distances and scale invariance, blah blah blah. And second order transitions are more interesting because when you study second order transitions, you study them from the framework of some kind of field theory. And when you're doing this, you the whole analysis is done actually away from the critical point. So you're looking at how the effects of the degrees of freedom that go critical at GC kind of extend into larger regions of parameter space. And then all these kind of conformal field theory methods and all this stuff that you can use to study them. So they're much more interesting. from a theoretical point of view, and also from, there are many more like techniques that you can use to study them from an analytical perspective. So the traditional framework for understanding second order phase transitions is Landau, Ginsburg. Maybe I should add like Wilson Fisher here. Landau, Ginsburg, Wilson Fisher theory. And Landau, Ginsburg is as follows. You assume that the two phases that you're interested in differ by some spontaneous symmetry breaking, right? So you have some symmetric phase, and then you have some like spontaneous symmetry breaking phase, and there's some operator which is charged under symmetry that gets an expectation value. If we let that operator be phi, then kind of the assumption of Landau-Ginsburg theory is that the critical point is constructed in some kind of quantum field theory or just regular field theory built from this order parameter, right? And so the prototypical example of this is, of course, this phi to the 4 theory, right? And this is like the only reason why condensed matter people care about quantum field theory, right? It's super important. I don't need. It's hard. It's basically impossible to overstate like how important this kind of action is for doing physics, right? So, okay, so given this, it's important to know like what the limitations are of this approach to understanding second order phase transitions, right? So one limitation, it's not really a limitation, is topological phase transitions that involve topological distribution, or really things that involve gauge theory, something like this, right? So in these examples, the order parameter that gets an expectation value in the symmetry broken phase is non-local. So it could be some Wilson loop, something like you have some e to the I integral of A, where A is a gauge field or something, and this is getting an expectation value. But this is not really. This is kind of violating the assumptions that went into Landau-Ginsburg theory, right? So you can have second order transitions in these theories, but it would be kind of like ridiculous to try to write down some kind of action like this that's like integral of like d e to the I, something like this. Like what the hell is this, right? This doesn't make any sense. So there's no like local action that we can write down in terms of these order parameters. And so these are examples of phase transitions that aren't captured by Landau-Ginsburg theory, but Landau-Ginsburg was not pretending to be able to describe them in the first place. Slightly more interesting is this example of deconfined quantum criticality, which we heard about last week. And kind of the general setting of deconfined criticality is that we do have a phase transition that involves local order parameters that are getting local order parameters that are getting expectation value, but it happens in a way that would not kind of be predicted by Landau-Ginsburg theory, right? So, for simplicity, we consider this example, and as Robert was telling us last time, you have these two different order parameters to get expectation values. So maybe here we have phi 1 getting an expectation value. Here we have like phi 2 getting an expectation value. Here's some parameter that we're tuning G, phase 1, phase 2. But what happens in deconfined criticality is that the critical point is that tunes between these two phases is such that phi 1 and phi 2 both go critical at the same time. If we were imagining this happening in the context of some kind of Landau-Ginsburg theory, we would expect this to only be possible in like a set of measure 0 in parameter space, right? So suppose we had, we have some situation where we have these two order parameters, and we're considering a phase transition where they both go critical at the same time, right? Well, if we were going to write down some kind of Landau-Ginsburg sort of action for this scenario, right? You can imagine, so we'd have to write down some, potential for phi 1, phi 2 that would appear in the action, right? Oh, sorry. But this potential, suppose for simplicity that phi1 and phi2 are both getting, they're both like Z2 fields. So the symmetry that's getting broken here is Z2, right? So you know, maybe the potential for phi1 would look like this, right? And you know, by tuning this between this shape and this shape, right, I can have a second order transition for phi1, right? And if I also had this kind of exact the same thing for phi2, right? Maybe this. Oh, sorry. This is like phi1. I'm trying to draw like the potential, like the phi to 4 potential of these two fields, right? Here's phi2, and then this would be like a surface of, just imagine of revolving this about the z-axis, right? Does this kind of make sense? I'm trying to draw a 3D version of this, like the Mexican hat potential, right? I don't know. I don't know if this is intelligible or not, but what would happen if both phi1 and phi2 were going critical at the same time is that you would have to have like the potential for phi2 and the potential for phi1 both going critical, meaning like this, right, at the same value of the param at the same time, right? And so this is only possible if you fine tune the potential such that it's kind of like symmetric between phi1 and phi2, right? If you consider generic changes of parameters which are changing these potentials for these fields, then generically what happens is that one of them goes critical first and then the other one goes critical later, right? Or vice versa. But deconfined criticality is an example where, in fact, you have like a generic way of having both of these phi1 and phi2 fields going critical at the same time. And the reason why this is possible is because in this example, phi1 and phi2 are not really like independent fields, in that you know, their order parameters are kind of like not communing with each other. And if you try to write down phi2 in the description where phi1 is local, then phi2 is non-local. And so it's impossible to write down in the case of deconfined criticality. It's possible to write down an action where both phi1 and phi2 are local. And so you can't write down any kind of Landau-Ginzburg action for these fields. So in that sense, it's kind of violating the assumption of Landau-Ginzburg theory again, because Landau-Ginzburg theory requires you having these local fields transforming under the symmetry. Yeah. I'll stop for any questions if people have questions. I don't know. I also want to make sure I'm not just like talking into the void, like people can hear me. Is that true? Okay.
Yeah.
I have a thumbs up.
Yeah, you're good. You're not talking into the void.
The deconfined criticality thing. Am I going too slow or too fast or what?
I think it's a good speed. It's a good like review
Okay.
of what happened last time.
So okay.
So I guess one question I might ask is when we say like happens because ordering in phi1 looks non-local in the phi2 description.
Yeah.
This is related to fractionalization. Yeah, like, so does that like sort of generic description necessarily imply like fractionalization at the critical point?
I don't know if it necessarily implies fractionalization. Like I think you can construct examples in gauge theories or something where you have well, I don't know. So one problem, right, is that the number of examples of systems that kind of do this deconfined criticality thing where these two parameters are non-local is not, from known examples, isn't that big. But I don't know. I don't know if the fundamental thing has to do with any kind of like description in terms of fractionalization. Like fractionalization, I mean, it's kind of like a matter of the way you look at things. Like it may be convenient to work with to have the fundamental
Right.
degrees of freedom going into your action be described in terms of fractionalized stuff, right? But that may not be the case, right? In this example, we have in the example the order you have like legit gauge invariant, if you will, order parameters that are actually getting expectation values on both sides, right? So it's not as if the degrees of freedom which are getting expectation values or something are themselves fractionalized. It may be that a fractionalized description is useful at the critical point, but in terms of just describing the two ordered phases and the fact that there's a transition between them, this general kind of setup of Landau-Ginzburg here does not require any specific part-time description. Right?
Got it. Got it. Thank you.
I might have a really basic question. So the fact that one of these things looks non-local and the other one would make me think that there would have to be some kind of special or unique coupling. And just because I don't know enough of the examples, is there some either characteristic coupling that you tend to see in example or in like Hamiltonians that display this? Or is there some like other metric other than the explicit expectation values, like the end result of looking at all of this, that tends to be like, I don't know, foreshadowing of what's to come?
Are you asking like if I tried to write down like the quantum field theory, like describing this transition, what would be special about it? Like what kind of, how are these degrees?
Yeah, basically, like if you see a quantum field theory and you have some like wedge operator or something, then you start questioning whether or not there's some weird boundary stuff going on, or I don't know, if you have some kind of super entangled ground state, then you might wonder if there's some kind of effective gauge theory going on. I'm just wondering if there's some other intuition about, like, prior to going through full analysis to see that there's deconfined criticality, if there are any telling signs either in the structure of the Hamiltonian ground state or anything else.
Yeah, well, so the normal thing that people would say here is that like the as Robert was talking about, can I not? I don't know how to mute my iPad. Anyway, as Robert was talking about, it's like if you consider defects in one order parameter, they carry charge or order parameter. I remember like the VBS example, right? You know, vortex of one or vortex of the VBS order parameter has a spin and stuff like this, right? So you can show that the fact that the vortices of one order parameter carry charge of the other order parameter kind of implies this non-locality, well, not mutually non-locality stuff that's going on at the phase transition. So I would say that the kind of thing at the level of just kinematics, just like symmetries and stuff, talking about what the detailed form of the action or Hamiltonian is or anything like that. It's this, you know, the fact that these two symmetries, the defects of one are charged on the other, is essentially what implies all this stuff that happens at the critical point. So I think you could say that, like, yeah, if you look at the symmetry defects of these two symmetries and one is charged on the other, then you're not going to be able to write down this kind of local Landau-Ginzburg thing. So in this way, it's kind of like violating the assumption of Landau-Ginzburg theory. In the Landau-Ginzburg theory is like the critical fields are each charged on their own symmetry and they're not charged under any other symmetry and stuff like that.
Awesome, thanks.
Yeah. Cool. So these two examples are like telling you that Landau-Ginzburg theory is not everything in terms of classifying second order phase transitions, but Landau-Ginzburg theory did not pretend to be able to describe these two phases. Okay, so then what this talk is going to be about is that really should be trilateral theory, but are not. So in these examples, we're going to have the symmetry actually is just going to be Z2, and we're going to have a symmetric phase, and we're going to have a spontaneous symmetry breaking phase for Z2 symmetry as a function of some parameter. And that's all. But we're going to show that the critical point here, which is the second order phase transition, is not describable by Landau-Ginzburg theory. And so this is like kind of more serious because we're going to have a local order parameter that's going critical, and there's not going to be any there aren't going to be any like anomalies or two order parameters with different charges, blah blah blah. There's not going to be any like topological stuff. It's actually going to be example of something where Landau-Ginzburg theory should work but doesn't. Right? So if you had asked a standard condensed matter theorist, I guess, before our paper came out, or indeed after our paper came out, because very few people I think actually read it, and you told them you had a Z2 spontaneous symmetry breaking transition with no like topological blah blah blah. They would, and it was continuous. They would say, okay, I know what this transition is. It's the Ising transition. I know all the critical exponent because Ising has been studied to death. But in fact, we'll see that there is a transition here that is not the Ising transition. And so the kind of moral of the story here is that on one hand, this might be a bad thing because it tells you that we don't actually understand second order phase transitions, the way of thinking about second order phase transitions as well as we thought. On the other hand, it's interesting because it gives us lots of cool stuff to think about. Right? So okay, so let's go. Now I'm going to talk about the example that one example of such a phase transition. Okay, so let me talk about the strategy of how we came up with this thing, right? So if you really like quantum field theory and you don't really care about doing things that are realistic for the point of condensed matter physics, one way to kind of look at interesting phase transitions is to, normally, this is kind of what I was saying at the beginning. Normally, you would, when you're thinking about phase transitions, you would like you would find some phase one, and you would find some phase two, and then you would try to figure out what kind of phase transition can exist between the two phases. Here we're going to do the opposite, and that we're going to start with some quantum field theory that just we're going to pick out this quantum field theory by hand, and then we're going to see if this quantum field theory can actually be interpreted as a second order phase transition between two orders, or between two different phases. And we're going to try to figure out what these phases are. And this is nice because there are jillions and jillions and jillions of QFTs out there. You can pick your favorite one and see if it makes sense as a second order phase transition. Okay, so one example that condensed matter physicists know that it kind of illustrates this philosophy, which I guess is probably, I'm supposed to tell you. I think I'm going to tell people about SPTs in December. So this slide is kind of like a little bit jumping the gun. But for those of you that know about like topological insulators, this slide is for you. So this kind of strategy is one way of thinking about topological insulators. So we're going to be in 4 space-time dimensions, and we're going to start with the quantum field theory that's just a free Dirac fermion, right? And so in this picture that I drew in the last slide, here we're going to interpret this free Dirac fermion as a second order phase transition separating two different phases. Okay, and what are the two different phases? Well, the parameter that we're going to use to tune between these two phases here is going to be the mass of the Dirac fermion, since it's negative and not cause problems. And so it turns out what happens is that when m is very large, very, very positive and very large, and when m is very negative and very large, you actually have two different phases. When m is very positive and very large, well, the two phases differ by an SPT, basically by a topological insulator, which you can show by looking at the response of this theory to a background gauge field. Yeah, I guess I don't know how much I don't know if people already know about this or not, but what happens is that if you couple this theory to a background gauge field for the particle number symmetry here for psi, so you replace this derivative with a covariant derivative, then what happens is that the m being very negative phase is just trivial. I just have infinitely massive Dirac fermions, and the IR is completely trivial. But the phase where the mass has the opposite sign is actually non-trivial, and it's non-trivial in the extent that the partition function as a function of this background field is equal to this expression here. So this expression is the theta term that people are probably familiar with, right? And f is the curvature of this background field. So the two phases are different, and yeah. So then we can interpret this Dirac fermion as a critical point between these two phases. Do people know about this? This f this way of thinking about TIs is that? Okay. My gives me feedback. So I'm not going to explain where this formula comes from, but just remember for the rest of the talk that if I have a Dirac fermion, if I have fermions, fermions with very large positive mass and very large negative mass differ by their response to this background gauge field. Okay. So the example that we found that illustrates this kind of phase transition that goes beyond Landau-Ginzburg theory is basically like is the same spirit as this topological insulator thing, but we start with non-abelian gauge fields and a bunch of fermions and blah blah blah. So we're going to start with we're going to pick a QFT, right? And we're going to think about it as the second order transition between two ordered phases. And the QFT we're going to pick is this guy. So this is we have NF fermions. So this I index runs from 1 to NF. And each fermion is going to be charged in the fundamental representation of SUNC, where NC is another parameter that we can control. And we're going to couple them to this dynamical SUNC gauge field. So this is the Yang-Mills field strength for the dynamical gauge field. Here's the Dirac fermion, right? And then as in this topological insulator example, the parameter which we're going to use, I already have this picture here. The parameter which we're going to use to go between these two phases is the mass of the fermions. Okay, so what we're going to do, since we're really just interested in like seeing if there are violations to Landau-Ginzburg theory without caring about their physical relevance, we're going to allow ourselves to make N, C, and F be whatever we want. And in particular, we're going to make them, we're going to choose NC and NF such that when this mass is 0, when we just have this massless field theory, it is free in the IR, meaning there's no confinement in the IR. So recall that right, if NF was like say 2 and NC was 3, like in strong interactions, we know that the strong force is confining at long distances, right? And so it's strongly coupled in the IR, and it's hard to deal with. But what fermions do is they screen the gauge field, right? So if I put some what the matter fields do, the matter fields will come in here and like screen the charge, right? Hopefully people have seen some picture like this, the charge. Okay, so the matter fields come and they kind of like this charge polarizes the vacuum, and then when you look at long distances, this kind of charge is screened down to a smaller charge by virtue of these fermions. So if I add enough fermions, they can actually change the beta function of this non-abelian gauge theory such that the gauge coupling is smaller in the IR. And what this means is that in this phase, in the IR, the gauge coupling is very small, and so we just have basically free fermions. And the fermions in the gauge field are decoupled. And so this theory is something that is very easy to think about. Okay, so the context of in what is going forward, we're going to have this theory where at the massless point we just have this very simple IR free theory of a bunch of Dirac fermions. Okay, and then just like in this topological insulator example that I talked about, we're going to try to identify two different phases on the two different phases that occur as I change the mass. Okay, and this is going to give our example of this beyond Landau transition. Okay. So this sounds, let me just put this in perspective of where we're thinking about. This is kind of like a very centillian philosophy, I guess, but the kind of like philosophy about why we're studying this kind of examples as follows, right? We're not really thinking that we're actually describing some kind of crazy QCD theory, right? And we're not imagining that condensed matter physicists are going to go out with some QCD stuff in the lab and we're going to look at the phase transition of this QCD, right? What we're actually imagining is that we have some UV lattice model that in this case is a bunch of bosons that are hopping around on some lattice in some very complicated way. And in kind of at intermediate scales, they're described by this gauge theory that I wrote down on the previous slide. And then, yeah, and so our task is to figure out what happens at even larger scales. But that even this kind of gauge theory stuff seems kind of fanciful, right? It's kind of the spirit of this is the following, you know, this everything not forbidden is compulsory. I forget who said this, but I think maybe it was Gelman or something. But yeah, the idea is we cooked up this crazy quantum field theory, and you know, given that the number of complicated lattice models that we can write down is huge and infinite, right? There must be some lattice model that we can write down such that at intermediate scales, its effective description is given by this field theory that I wrote down on the previous slide. Right. So this is kind of the setting that we're working in. Okay. Actually, does anyone have any questions at this stage? 5, 4, 3, 2, 1. No questions. Okay. So yeah, maybe I don't even know if I want to mention this. So basically, what we're back here, what are the symmetries of this action? You know, I told you that we have some symmetry breaking phase transition, so we need to say what the symmetries are, right? One symmetry that we clearly have is flavor symmetry of these fermions, right? So we have NF fermions, right? So you know, I have a symmetry where I send, you know, psi I goes to U I J psi j, where U is some unitary rotation, right? So I have flavor rotations between the fermions, and then importantly for us, we also have time reversal. So time reversal, which is a Z2 symmetry here for us. Yeah, and this is, you can easily check that this action is time reversal invariant. And if we have the symmetries of flavor and time reversal, then the only term that we can add to this IR action, the only parameter that we have to tune here while preserving the symmetries is this mass for the fermions, right? So yeah, we only have one parameter that we can tune while preserving the symmetries. That parameter is mass, and so we have this picture. Okay, so what happens when we tune this parameter between different values, right? So recall what not slide about the topological insulator. If I make the mass of the fermion very negative, then the fermions just are massive and we just throw them away. They don't do anything in the IR. And what we're left with is just the gauge fields, right? But the gauge fields by themselves, without any fermions there to do this screening that I was talking about, the gauge fields by themselves just are confining, right? Because this is non-abelian gauge theory. And so in particular in the IR, there's nothing. If you look at long distances, like if you just had pure gauge theory, you know, SU3, whatever gauge theory, and you looked at long distances, there's nothing interesting because it's gapped. So the IR is totally trivial. So maybe I can write down this phase diagram again. Here's M. When whatever. When M is very negative, we just have trivial gapped vacuum over here. Okay. Now, on the other hand, what happens when we make M very large and positive? Well, just like what I said with the topological insulator, when we have a very Dirac fermion with a very large positive mass, and we integrate it out, if it's coupled to a gauge field, it produces this kind of term for the gauge field, this kind of theta term. And I asked you just to believe me on this. The difference between the here and the direct fermion was with this topological insulator example I was giving, the gauge field you coupled to it was just a probe field, right? It was not dynamical. Whereas here, the gauge field we're coupling to, is this SUNC gauge theory. So, which is dynamical. It's integrated over in partition function. So the action at very large M is this, and we know that this guy up here. I just told you that this is just pure gauge theory, and it confines, and so it's trivial. But this guy is actually interesting in that we don't actually really know what this trace of this theta term does. It gives, I don't know how in how much detail to go, but confinement here is kind of confinement in this pure gauge theory is caused by these these kind of topological textures for the gauge field. And what this extra term here that we get from integrating out the fermion does is it gives these topological textures different phase factors. This is the topological charge for people who know what that means. And so this is like e to the IQ as it appears in the partition function. So this gives like phases to the instantons, which can cause some interference and stuff. Anyway, it's kind of unclear exactly what this theory does in the IR. So at the moment, this is a question mark over here. Okay. Yeah. Okay, but we can actually make progress we can actually identify what this question mark over here is with some arguments that are maybe a little bit too high tech for the present setting. But I don't know, in the spirit of just maybe telling you what happens and maybe not explaining too much why things happen, is that yeah, we could. It turns out there's an anomaly between a symmetry coming from between something called a one-form symmetry of this gauge theory and time reversal. Maybe I don't have to explain exactly what's going on here, but it's kind of the same thing as what happened in the deconfined criticality example we were talking about. You had these two order parameters that defects of one carried charge of the other. These two symmetries that were like this, and it turns out in this example there's kind of a similar thing where this one-form symmetry thing of the gauge field and time reversal are defects of one kind of like carry charge of the other in some sense. Anyway, maybe I won't explain exactly how this works. You can of course ask me later if you want to go into this in detail, but you can argue that let me see. Yeah, you can argue at least when NC, the size of the gauge group, is relatively large. By large, I mean like 4 maybe, or larger. You can argue that what happens is that this question mark that I wrote down over here, this is trivial. This question mark is for sure a phase where time reversal symmetry is spontaneously broken, but nothing else happens, right? So we have the Z2 symmetry. Remember, time reversal acts as Z2. Here's M. And you can show that, yeah, so you can show that this phase here is just a time reversal symmetry breaking state, and there's nothing else going on. Again, for examples for reasons that I can explain later if you're curious. Let me just skip this. Yeah, let me just skip. Okay, so if you believe what I just told you about this time reversal symmetry breaking thing, then what the picture for this critical point is as follows, right? We have time reversal, spontaneous symmetry breaking. Okay, and so given that we have time reversal, spontaneous symmetry breaking over here, let's try to understand if we can have a Landau description of this critical point, right? So the way I presented this critical point here was in terms of this complicated gauge theory with a bunch of fermions and stuff, right? But that's just one way of writing down the theory, and there may be other ways of writing it down. So that is not the gauge theory that I wrote down is clearly not a Landau description, right? Because there's no local, well, for reasons that I'll get into, but it could be that there are different, maybe there's a different way of writing down the theory or something that looks like a traditional kind of Ising type Z2 spontaneous symmetry breaking thing at this critical point. But in fact, this can't happen for the following reason. So I told you that T is spontaneously broken over here. Well, that means some operator charged under time reversal is getting an expectation value. So we can look at all the operators that appeared in this fermions plus gauge fields theory that we were considering, and look for ones that are charged under time reversal, right? And so the one that you find is this here. So gamma 5 is this, in the vial basis here, it's this matrix. This is the chiral mass for the fermions, and it's odd under T. And so what happens here is that this phase is identified as in this fermion gauge field description that we were talking about, is identified as this guy getting some non-zero expectation value. Okay, but then we can prove that this is incompatible with having some local Landau-Ginzburg action of this form at this critical point. And there are a few reasons. One reason is that you can calculate the critical exponents in the theory in this second order phase transition, and they are very different. Well, here they are. They're very, very different from the Ising critical point. They're actually extremely different from the Ising critical point, which means that we're not just having some Z2 charged thing that's getting an expectation value. Another reason, another reason is that remember I told you there's this flavor symmetry of the fermions, right? We have NF fermions and there's a flavor rotation of them. It turns out that at this critical point you have operators which go critical, like this Dirac mass, which are this chiral mass, which are charged under this flavor symmetry. And so what this means is that at this critical point, you have degrees of freedom which are charged under G that go critical. But G is not, this flavor symmetry G is not the symmetry that's getting broken. And so what Landau theory would predict is that all the degrees of freedom which are going critical are the ones that are charged under time reversal, but that things that aren't charged under time reversal and that are instead just charged under this flavor symmetry group, for example, do not go critical. Anyway, so there are some reasons. I mean, just by looking at this point and seeing that there's this crazy gauge theory, maybe it's kind of intuitively obvious, but there are reasons that you can why this thing is provably not describable within this Landau-Ginzburg framework. Okay. And so maybe two slides before I finish, just to kind of give you a here's what the phase diagram that we are that we kind of derive. Okay, so here's what the phase diagram looks like. I've kind of been drawing this in various guises through the past few slides. This is now plotted as a function of temperature and the mass, which is the tuning parameter, right? As I said, when the mass is very large and negative, we just get some kind of very boring. It's just pure gauge fields, and they confine, and nothing is interesting. Whereas when the mass is very large and positive, we have this confined, and this is spontaneous symmetry breaking, right? And then the kind of usual, we were kind of talking about this a little bit last time. The usual quantum critical fan stuff that you can learn about in Sachdev is also appears here, and can write down that within this critical fan we have this this gauge theory, massless gauge theory that I was talking about, and the kind of shapes of these crossovers and blah 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 all follow from the gauge theory that we wrote down. So this is kind of the picture, and then just last comment is how this kind of fits into a broader framework, right? So what we are we're studying a phase transition between this Landau ordered phase where time reversal, i.e. Z2 gets spontaneously broken, and the trivial phase. And the transition that we described was this guy here, calling it a deconfined quantum critical point because it's described in terms of these fermions, which are charged under a gauge group, and so they're fractional for the usual reasons, and blah blah blah. We have some crazy thing over here, and this phase transition, which is robust, is what I've been describing. But presumably, if you change some other parameters in the microscopic UV lattice model, you can get between these two phases by using the traditional Ising Z2, studied to death the traditional Ising Z2 transition with the regular Ising exponents and stuff. So if you were to look at an all parameter space, we have this kind of scenario. And so the kind of broader message here is that, if you have phase 1 over here and you have phase 2 over here, and you assume that, phase 1 and phase 2 differ by some spontaneous symmetry breaking, and you assume that the way to get from one to the other is, described by a second order phase transition in terms of some order parameter that is charged that gets a expectation value. This kind of line of phase transitions does not all have to be what you would expect from Landau-Ginzburg theory, right? You could have over here, this region of transition over here could be like some Landau-Ginzburg theory, and then over here it could be like something else, some other theory M or something, and over here it could be some theory M prime or something, blah blah blah. It seems like there's no real rule that tells you what has to happen when you go between these two phases. And so the moral of this story is that when we're trying to classify phases of matter by ways of going between phases, it's actually kind of like, this is probably going to be actually incredibly hard to do. Like this program of attacking things, well, who knows how hard it is to do or not, but it's certainly harder than we expected, right? Because even if we assume that this line here is second order, it could be many different ways with distinct critical exponents and distinct universality classes and blah 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 going between these two phases. So that's kind of the point. And yeah, so that's kind of the point of this work. And going forward, this was done a few months ago, and I haven't really been working on this stuff recently. But what we would, if anyone thinks this stuff is cool, like what we want to do in the future, they're kind of like open questions, right? One is like, does there exist like less exotic examples, right? So we had this very, the critical point here is very fancy, crazy, SUN gauge theory, blah blah blah. So it would be nice if there were some less esoteric examples, and there are also lower dimensional examples too. So whether this phenomenon we described is relevant to 2 dimensions or 1 dimension, I think so. We found some like almost examples in 1 + 1 dimensions, but it would be nice to know if there was some kind of like fundamental, more fundamental way of understanding when this happens. Here we just give an example. Anyway, I have a whole bunch of other crap here on SPTs, but I think that's not really relevant. So I'll just stop here, and then, yeah, if anyone has questions, we can talk about it. Thanks.
So I think you alluded to that, like, obviously you're not trying to think about this physically, but I know in that one phase diagram you have, like in the UV, you have some sort of hopping bosons.
Oh, yeah.
So is there any way we might hope to see a phase transition like this?
Like you're asking me what is this when I say UV boson's complicated? What, like, could I construct an example?
Do you have a handle on that, or it's just
Yeah.
some.
I would say this is classified under the open questions.
Got it.
Because yeah, so the philosophy. The philosophy here, there are two approaches you can take. The approach we were taking is just a matter of principle. Like, just as a matter of principle, you have this order parameter getting of f. Is it describable by Landau Ginsburg? And so we're kind of coming from like a top-down perspective where we just like choose a field theory by hand. And I mean, you can cook up like really stupid examples, like where you have, but I mean, you're not gonna have like MC spinful bosons with a large number of flavors.
Yes,
have some parton description where the parton gauge fields are like these SU2, right? This is like we want to find less esoteric examples. I guess the another way to say this is we want to find a UV, maybe a UV model that's not crazy that we can argue exhibits the space transition. Yeah.
And I guess another, so you alluded to dimensionality here. Is there I guess if I'm just thinking about, being in higher dimensions, one might expect this type of thing to happen more often due to like higher, more freedom to choose your theory.
So the reason why we were doing in 4 dimensions is because in 4 dimensions, gauge theories are easy, or so we were using gauge theories as a description of the critical point, because then you can get something that is very like obviously not Landau Ginsburg, right? If you have these kind of right. So we were kind of going into this from the framework of let's find something weird. So let's assume that a critical point is described with a gauge theory. But then, if you go to very low dimensions, like 1 + 1 dimensions, gauge theories are like not interesting. You don't have any dynamical degrees of freedom. And if you go to 2 + 1 dimensions, gauge theories are still interesting, but they often tend to just totally confine.
Right.
Right. And so we've had to work in 4 dimensions because we want to describe things in terms of gauge theories, but that's not. If you're willing to consider examples that have, Fermi surfaces and blah, 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 then
okay.
Yeah, you can work in different dimensions.
Yeah, okay. Interesting. So you would get some kind of Fermi surface of partons, like when you're thinking about the deconfined quantum critical point.
Yeah, so the goal is just to the goal would just be to try to write down, like in 2 dimensions or something, to try to write down a theory which is described in terms of some emergent gauge. Pick some theory that has emergent gauge field or something and is tractable in the IR, where you actually know what the IR theory is, right? And then try to see if there's some like parameter deformation that you can add to that theory that takes you into a spontaneous symmetry breaking phase or into a trivial phase. So then you have to then you have to look at the kind of examples of deconfined, of interesting like gauge theory like stuff in 2 dimensions that you know of, and then play around with them.
Cool. I think Dan I think I might have seen Dan have a question.
Just want to make sure I understand. So in this specific example you gave, so you have a fermion flavor symmetry G, which is not broken, right?
Right.
But this fermion symmetry is actually emergent IR symmetry, right? Because you have because in UV all you have is some boson theory.
Yeah, that's right.
So I'm wondering, like, what's the importance of having such an emergent IR symmetry?
Right.
So,
Yeah. So
sorry. So for usual Ising transition, so say in some spin model, all the symmetry are considered as a Z2 symmetry, but here in IR, you actually have a enlarged symmetry, not only Z2, you also have this G symmetry, right?
yes, that's right. Yeah. Yeah.
So
So
yeah,
so yeah. So this is kind of like the last half of the talk that I didn't get into. So the thing with this G symmetry is as follows, right? So the symmetry is there, and we are this this flow here that I've been describing that goes through this DC QCP assumes that you have this symmetry, right? But
yeah,
yeah, right. But the symmetry is not broken anywhere,
yeah,
right? So so the symmetry is not participating in the critical point, if you will. And furthermore, one thing you need to check is that you know, there are no like SPTs or anything for the symmetry, like that these two phases here are not distinguished in their response. These two phases treat this G symmetry in the same way, right? If they treated them in different ways, then there's something else going on, you know, that is, and then like if you had an SPT for this G or something, then it would be beyond Landau. So what you need to do is you need to check by, you know, coupling to background G case fields and stuff that the G is, nothing is changing with respect to the G symmetry as you go on here. So from this perspective, it seems like this extra flavor symmetry is not essential to having this kind of transition that we talked about, right? Because it's not participating in any of the criticality in any way, and it's treated the same on both sides. We tried to find an example where the only symmetry in the IR is Z2, this Z2 that's getting spontaneously broken, right? But yeah, so somehow we weren't able to find it because we're working with these gauge theories, and we want them to be tractable in the IR, so we have to have a very large number of fermions and stuff.
right.
And so if you don't add these extra symmetries, it's just becomes hard to analyze because there's so many different perturbations. Yeah, let me add that here, like any other like ingredients necessary, right?
Yeah, I guess although here the G symmetry doesn't seem to play any role, but if you consider different symmetry, then it seems that the Hilbert space are totally different. You should consider if the symmetry is enlarged, you should consider the fields carrying some representation of the symmetry. It could, I mean, so in this specific example, if the G symmetry is necessary because you want to stabilize the critical phase, right?
Yeah, the G symmetry is just so that there's only one parameter to tune, right? Like if we didn't require we had this flavor symmetry, right? Then there would be a bunch of other masses that you could add, right? Just the parameter space here would be more than one dimensional, right? You wouldn't just have the Dirac mass. You could add a bunch of fermion masses that broke this flavor symmetry, right?
Yeah.
Then things.
Yeah, I guess I'm just trying to think about what's the necessary input for you to identify a phase, a critical point between two between a trivial phase and between the solar phase and the spontaneous symmetry breaking phase. It seems that maybe you don't just need the symmetry breaking pattern. Maybe you need something more.
Yeah. So I think that the point of kind of going through this whole stuff about SPTs and blah 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 was to say that the information that you need to describe 1 and 2, these two different phases, does not care about G in the sense that like this is just G symmetric and this is like G symmetric. So like in this example, G is some flavor, you know, some SP and blah 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 for these fermions, right? But I mean, I don't, certainly it shouldn't depend on what G is, right? Like that nothing involved, this phase diagram doesn't depend on what the actual group G really is, right? Like G is not doing anything anywhere. So
yeah, but if you don't,
it would be kind of weird if you said like we have this phase transition between phase 1 and phase 2, right? But this only exists if you add an extra symmetry group that is trivial in all of the phase diagram, right?
yeah, but it seems that from the example you gave, this is the case, right? If you changed the G group to a much smaller fermion flavor, then you won't have the fixed point, right?
Yeah, it just becomes, I mean, it's basically just we haven't looked into this in detail, right? But it's basically because, yeah, so if you don't require this flavor symmetry, you can add many more Dirac, well, you can add many more mass terms, right? And then when you integrate out the fermions, right? We don't actually know what the full story is, right? Because when you integrate out the fermions, in this case, you know, you have a bunch of different mass terms you can add, and these mass terms, when the fermions are integrated out, will generate response terms for the gauge field, right? But the response terms they integrate they generate are not just, you know, trace of f wedge f, right?
Yeah.
They can be twisted with some representation matrices stuck in here and stuff like that, right? And so, well, I don't know that letting you add these extra masses would actually take this phenomenon away. It's just that the analysis would be complicated, and so we actually haven't done that yet. So we don't really know what for sure would happen there. But yeah, you're right. The technical statement is we're going from a G cross Z2 phase to a symmetric, right? To a G phase, symmetric phase. This is the transition.
Yeah.
And the only thing that's actually being broken and stuff is this. But there is this extra thing here. So yeah, so understanding what this is doing is a question that would be good to answer. But, you know.
I'm just thinking if I want to understand, if I say I want to classify all the Landau, all the beyond Landau phase transitions, like how should I, like what's the input? Say if I want to classify all the bosonic SPT phases, like Xiaogang told us what we should do, like what are the inputs,
right.
but here I'm not sure.
Well, that's the point, is we don't know what the inputs are yet, right? So I painted in this picture where if I know we have the second order phase transition between these two things, we can have a bunch of different possible ways to go between these two, and we don't know what the input data is for like distinguishing these two. Of course, that would be a great thing to know, right? With regards to this G, it's not really clear because like there's no mixed anomaly between these two symmetries or anything. Like there's no topological reasons. Like from the perspective of kinematics, this G doesn't do anything. So at least if you look in terms of like anomalies and other kind of kinematic stuff that we are familiar with, I don't know. It seems to just be random. So
yeah, I think it seems to be a byproduct because you have a mixed anomaly between time reversal and this one form symmetry, right? But then the fermion carries the fundamental representation of G, and it also carries some gauge charge.
Yeah, that's right. Yeah, but I mean the one form is like that's not really built in. Yeah, I mean that's just a product of our description of the critical point, right? But yeah, but yeah. I mean, we don't know. Well, all that exists right now is this like example, but we don't know how this fits into anything. Don't know any kind of like more general theory.
Yeah. Yeah, I don't know. Yeah, it's interesting.
Cool. Any other questions? Last call. All right. So thank you, Ethan. That was a good talk, and it's good that we're recording these. I think I will come back to this in the future, especially after the SBT talk you give. I can watch them in reverse order. But thank you again.